The topic of this video is a general overview of acids and bases and basic acid-base chemical reactions. For our purposes in biochemistry, most of the nomenclature we use around acids will follow the Bronsted-Lowry acid and base definition. In that definition, Bronsted-Lowry acids are molecules known to donate a proton or a hydrogen ion to solution when dissolved. So a stereotypical example of this is hydrochloric acid. When it's dissolved, it donates one hydrogen ion and one chloride ion. So by definition, it's donated a proton or a hydrogen ion, therefore fits the Bronsted-Lowry acid definition. Another molecule, sulfuric acid, contains two hydrogens. Under the right circumstances, when dissolved in water, it will donate one proton to the solution and then its conjugate negative electrolyte here, HSO4 negative. Another example with slightly more biochemical and biological assay relevance is phosphoric acid. So phosphoric acid, H3PO4, when dissolved in solution, under the right circumstances, will donate one hydrogen ion to solution, or one proton, and then its negative electrolyte here, H2PO4 negative. And if you look closely, you'll notice that this molecule, H2PO4 negative, still has two hydrogens attached to it. Under the right circumstances, these hydrogens can also be donated to solution. So H2PO4 negative can liberate another proton or another hydrogen ion, and then be accompanied by its conjugate negative electrolyte here, HPO4 negative 2. Alternatively, Bronsted-Lowry bases are molecules known to accept a proton in solution. So one of the classical examples of this, NaOH, we know sodium hydroxide, when it dissolves in water, will donate a hydroxide ion, as well as its conjugate positive electrolyte, a sodium ion. This hydroxide ion can accept a proton from solution to form water, or H2O. Another example would be ammonia. Under the correct circumstances, ammonia can accept a proton from solution to form ammonium. So we go from having a negative molecule here, ammonia. It combines with a positive hydrogen ion and forms the positive 1 ammonium ion. Another example is the nitrate ion. So NO3 negative 1. This can accept a hydrogen ion or a proton in solution and form the neutral HNO3. And if we think back to our example from the previous slide, H2PO4 negative, under the right circumstances, this molecule can also accept a hydrogen. So in this case, it would be referred to as a Bronsted-Lowry base instead of an acid. Here it absorbs a hydrogen ion and becomes H3PO4. So you may have noticed that when these Bronsted-Lowry acids and bases dissociate and donate protons or accept protons, they look very similar. This is because these molecules form conjugate acids and bases when they either accept protons or donate protons. So one example of this, a Bronsted acid that we've already looked at, phosphoric acid, when we dissolve this in water or a solution, we know that it donates a hydrogen ion, and as I referred to it previously, its negative electrolyte. When referring to Bronsted-Lowry acids and bases, we refer to this molecule as the conjugate base, because as we saw previously, under certain circumstances, this molecule can actually accept this proton to become H3PO4. So when these acids dissociate or pick up protons, they're labeled in pairs. So this is our Bronsted acid, and this is the conjugate base of our Bronsted acid. Similarly, a Bronsted base, H2PO4, like I just mentioned, can accept this hydrogen ion and become its conjugate acid, H3OP4. So depending on the direction of the reaction you're referring to, remember the joint relationship between Bronsted acids and their conjugate bases, and Bronsted bases and their conjugate acids. Now let's look at a slightly more complex example, or more specifically, the complete dissociation of phosphoric acid. So here's phosphoric acid, H3PO4 to start. We know when we place this in water, it dissociates into a proton and our conjugate base. So here is our Bronsted acid and its conjugate base. And again, if we look closely, we still have two hydrogens here. So if we attach a sodium to this molecule to make it neutral, this can be bought as a salt, and this is a compound that's used often in the lab to make buffers. If we dissolve this salt in water, first you can think of it as dissolving into its sodium and H2PO4 negative, the same molecule up here. But because we're interested in the dissociation of these protons, this molecule can, again, under the right circumstances, can donate that hydrogen to the solution, the surrounding water, and now our conjugate base for this is HPO4 negative 2, right? So our Bronsted acid has two potential ionizable hydrogens here, and our conjugate base has lost one. So again, a Bronsted acid and conjugate base pair. Now, if you look even closer, there is still one hydrogen left on this molecule. So you can buy this product again as a salt, and again it's used in the lab for buffers solutions. Na2HPO4. If we place this into water, our two sodiums will dissociate, and depending on the salinity and a number of other things in the surrounding solution, our HPO4 negative 2 can donate another hydrogen ion. So here again we have another Bronsted acid and conjugate base pair. So under the right circumstances, H3PO4 can fully dissociate all the way down to PO4 negative 3. But again, remember this occurs in steps. So we have our acid with its conjugate base, we have our acid with its respective conjugate base, and our last acid with its respective conjugate base. Now let's try this in reverse so we can associate Bronsted bases with their conjugate acid. So if we start with our PO4 negative 3 and it picks up a hydrogen ion or a proton, this Bronsted base has a conjugate acid of HPO4 negative 2. If HPO4 negative 2 is placed in water under the right circumstances, it can pick up an additional proton and become H2PO4 negative. Again, a Bronsted base with its conjugate acid pair. And lastly, H2PO4 in the right system and the right surroundings can pick up an additional hydrogen and protonate to become H3PO4. Again, remember, Bronsted base and its paired conjugate acid. Now let's try a little bit of a quiz. Here are a series of Bronsted acids and a series of other molecules. Which of the following is not an acid-base pair? That should be about enough time for you to take a guess. If you chose this middle example, you are correct. So H2CO3 and CO3 negative 2 are not a direct acid-base pair. Our example up here, HNO2, can dissociate and form H plus in solution and NO2 minus. And our methylamine down here, CH3NH3 plus, under the right circumstances, can lose one proton to become CH3NH2, a neutral compound. H2CO3 must first dissociate into HCO3 negative 1, right? So our Bronsted acid has lost one hydrogen, forming this conjugate base. And under the right circumstances, this can become a Bronsted acid and lose its last hydrogen, forming CO3 negative 2 and a proton in solution. So these two examples are not direct acid-base pairs. because of this intermediary compound here. Now, we've previously discussed strong electrolytes and weak electrolytes. If you hadn't heard it before, the same is true with acids. There are such things as strong acids and strong bases, as well as weak acids and weak bases. So over here, on the right, sodium chloride is a strong electrolyte. We know this fully dissociates in solution, and so does our magnesium chloride. Now, down here, our strong acid, hydrochloric acid, will fully dissociate into water, liberating all protons and all chloride ions. Similarly, sodium hydroxide will fully dissociate, releasing all of its hydroxide ions, forming a basic solution. This is not necessarily true with weak acids and weak bases. Weak acids and weak bases, such as the example from the previous slide, carbonic acid, oftentimes dissociate into their respective anions and cations, and this dissociation is governed based on some of the principles we've discussed in equilibrium reactions and incomplete dissociations. So this is a topic that we'll cover in another video, the principles that dictate how much or how little our weak acids and weak bases dissociate, and then how they balance out in equilibrium with each other. So for the last few slides, we're going to continue to refer to acids and bases in the context of being a strong acid or a strong base. Remember, these dissociate fully. And according to the Bronsted-Lowry acid definition, they either donate or accept a hydrogen ion. Arrhenius acids and bases either donate hydrogen ions or hydroxide ions. So, what is one way to measure how strong an acid or base or an acidic or basic solution is? If you hadn't heard of it before, chemists use the pH scale, which has a graphical representation over here. Typically, we think about this scale for being from 0 to 14. And if you're asking how to calculate the pH of something, chemists use this formula below, where pH equals the log of 1 over the molar concentration of hydrogen ions in a solution, or more simplistically, the negative log of the concentration of protons in solution. And again, remember, this has to be in moles per liter. So our pH equation here, pH equals the negative log of the concentration of protons in a solution. The pH scale, remember, is logarithmic. So the difference between 1 and 2, or a difference of 1 pH, is equal to 10 times that concentration. So the difference between a solution that has a pH of 1 and a pH of 2, the concentration of hydrogen ions is 10. A difference of 2 on the pH scale correlates to a 100 times difference in the concentration of hydrogen ions. So very quickly, what is the difference in concentration of protons, or hydrogen ions, between a solution with a pH of 2 and 7? You can simply count up the pH scale, 1, 2, 3, 4, 5, raise 10 to the 5th power, and that's a difference of nearly 100,000 times change in your hydrogen ions. So that's the difference between how many hydrogen ions in concentration are found in your blood versus your stomach, a difference between pH 2 and 7. That's massive. The pH scale also typically referred to in three different categories, where 7 is neutral, below 7 is referred to as acidic, and the further you get from 7, the more acidic this is, and then anything above 7 is basic. And again, the further you get from 7, the more basic a solution is. And since we've discussed pH, there's also a numeric concept that allows us to look at the concentration of OH, or the concentration of hydroxide ions in solution. This is referred to as pOH, the same function setup as our pH. It's the negative log of OH. Again, concentration of hydroxide ions in moles per liter. And if you hadn't been taught this before, the negative log of H plus the negative log of OH minus add up to 14. That is to say, pH plus POH always add up to 14. Let's do some practice problems calculating pH. So we're going to calculate the pH of a solution made by adding hydrochloric acid to water. We know that hydrochloric acid will fully dissociate into hydrogen ions and chloride ions. We know the formula for pH is the negative log of the concentration of hydrogen ions. So let's begin by calculating the concentration of hydrogen ions in moles per liter. If we add 0.03 moles of hydrochloric acid to a solution, we know through the stoichiometric balanced chemical reaction here that 1 mole of hydrochloric acid will dissolve completely into 1 mole of hydrogen ions. When we place this into our dimensional analysis, moles hydrochloric acid cancel, and we are left with moles hydrogen ion. If we divide that by the volume of our solution, 1.5 liters, you can do the math. We are left with 0.02 moles hydrogen ions per 1 liter water. So the concentration of our hydrogen ions is 0.02. If we plug this into our pH formula, we arrive at a solution with a pH of 1.7. Now let's try this if we've added 1 mole of hydrochloric acid into a solution with a volume of 0.5 liters. Using our stoichiometric balanced chemical reactions, we know these units cancel. We're left with moles hydrogen ion per liter. This comes out to be 2 moles hydrogen ions per liter. So H plus concentration is 2. Plug this into pH, and we have a pH of negative 0.3. Now remember, I've referenced the pH scale from 0 to 14. Technically, the pH scale exceeds these boundaries. However, we don't typically see solutions with pHs this high, or in this case, this low, below 0 or above 14. The rule about pH plus POH equal 14 still holds true. And if you're wondering why as biochemists we care so much about pH, pH is critically important for biological functions, biological macromolecules, catalytic activity of enzymes, and the protonation status of amino acids in proteins. We'll cover these in more depth in lecture.